what is all this about AI, and what is it we're talking about? AI is almost synonymous these days with deep learning, and deep learning is being used in a lot of places. For example, in object detection, for example, in self-driving cars. For improving speech recognition, we used to be statistical language modeling, and now we're using deep learning to improve it. In your home, in IoT devices, there are a lot of applications of deep learning and sensing what's happening around. And in language translation, Google famously improved the state-of-the-art in their language translation using deep learning and LSTMs. And of course, in healthcare and drug discovery, and the list goes on and on and on. But when you actually dig deeper to see what is it behind all of this innovation, it seems to be that the technology that keeps coming up is deep learning. So let's demystify this a little bit. Deep learning, in essence, is a neural network, a technology that has been around for a while. But the deep means it has many hidden layers of neurons. It's inspired by how the brain works. On the input layer, you put the input, be it language or, for example, a picture. And on the output layer, you ascribe some form of, for example, classification. Is there a cat in this image? And then you have a lot of labeled data, and you train this neural network so that it gets better and better at the trained data, but by virtue of doing that, it makes abstractions that allow it to also have pretty good performance on data that it hasn't seen before. So what's really interesting, though, is the function of these hidden layers in there. It seems that they are operating in a similar manner as how our brain neurons work. So let's try this out on your brains. This is a picture taken out of a window of our offices in San Francisco, and immediately when you see the picture, the window washing system was broken. You see some objects in this picture. How do you see them and how do you recognize them? It's just a bunch of colored pixels here. Well, it turns out how you do this is the second or third or fourth layer of neurons are really good at putting together some of these pixels and identifying edges. And then beyond that, there are neurons that take what these neurons are announcing as edges and putting them together into patterns, such as this cross pattern here. And then beyond that, how about putting some of these crosses together next to one another? There's some pattern there. And then taking those with some of the edges that we identified earlier, that's a bridge. And it turns out that not only is our brain operating this way and abstracting this way, but after we do this black box training of these deep networks and we interrogate that, the hidden layers there are making very, very similar abstractions. This technology, as I said, has been around for a while. In fact, the father of computing, Alan Turing, was one of the first to actually propose using neural networks in 1956. Some of what we are using today in neural networks have been around. For example, Schmid-Huber's lab came up with long short-term memory cells, LSTMs, that are used widely in time series analysis 25 years ago. In fact, he did an analysis just last year, a survey, and he announced that the original architecture is still the best architecture after 25 years. So what is it that is fueling this resurgence of interest in AI? There have been breakthroughs in the algorithms. It's not that the algorithms alone are still 25 years or 50 years old. We now know how to train and backpropagate these very large networks. But in order to do that, we do require a lot of compute capacity, and compute capacity these days is cheaper and more available. We need a lot of storage because there's a lot of labeled data that has to go through these trainings, and of course, we need the data itself. And we have been collecting the data. In fact, some folks have been collecting the data not quite knowing how they're going to get some ROI out of it, but now there is deep learning. And so this fuels this feeling that AI has ubiquitous applicability. We can throw any problems at it, and it can solve it. But not quite so fast. There are things that our current neural networks and deep learning cannot do very well. But before I get to that, let's look at another technology that has been around for quite a while that might be helpful in extending and expanding deep learning technology. Evolutionary computation, what was known as genetic algorithms, has been around for a while. In fact, the same guy, Alan Turing, came up with a proposal around evolutionary computation, which is inspired by biological evolution and survival of the fittest. And it was popularized by John Holland in the 70s. So how does it work? Let's say you guys have a website, and it has some traffic that comes to it, and you want to improve that website to some KPI, let's say the conversion rate of that website. The space of all possible website designs is multidimensional. I'll map it to 2 dimensions here. And you then run that web page, that design, or that variation to your current design against live traffic that's coming in. And you measure how well it's doing. What is the conversion rate for each one of these variations? And you try to get maximal coverage on your website, on your, search space. After a while, some of these designs are going to do better than the others. Let's pick a couple of these designs. What they've done is they've captured a combination of features in these variations that are doing better. If we take a subset of the combinations in what I'm calling parent A design and the other subset from parent B and put them together and build a child design and do the inverse with what's remaining and create a few children, chances are some of these children are going to be capturing the best of the 2 parents and therefore be doing better than both. And when we go through several generations like this, what we're going to end up is with performance that is consistently getting better. This system is evolving. It's adaptive because it's going against live data, and it's creative because it's coming up with new designs that we did not have in the past. Let's actually look at this in action. So I'm going to fast forward through 8 weeks of a system like this actually redesigning a website. This is a website that it was an educational website, and we want to optimize the number of people that are actually signing up on that widget on the left-hand side. So let's go through this system. It's going to try out different colors, different labels, different text placements, variations to the design that's already there. And it ends up with a design that is quite different than the original design that we had. Not just the color scheme, but the look and feel, the text. A lot of different things have changed here. In that process, after 8 weeks, we improved conversion by 45% out of a search space of 380,000. And that's a small search space relative to what the efficiency of an evolutionary computation. And all the while, it improved by 12%. Now, this system is not only improving the design of the page, it's improving the design based on the different users. So we don't want to have a one-size-fits-all. What is the state of the art of doing this? If we were to tackle the same problem using deep networks, we'd have to collect lots and lots of historical data and label them, so much so that it would actually range into the irrelevant. You know, your website and how it did, 5 years ago might be completely irrelevant to your business right now. And so by virtue of doing this, we built this model that segments the users, but that segmentation is static. As the problem statement changes, it does not change. So what if, rather than evolving the look and feel of the website or anything else that we're adapting, we were to evolve a mapping between what we know about the user that's coming to the site and what we want to show the user. So different users would see different designs. In fact, the same user might see a different design at a different time of day or day of week. And this mapping can change adaptively as the problem statement changes, as your content changes, and as your measurement changes through time. This is neuroevolution. This is evolving neural networks. And it can be applied to many different application areas. This is the same technology applied to trading in the stock market. And even though on the surface it looks like this automated trading system only made 2 or 3 decisions. It actually made many, many decisions that were keyed off of what is happening with this particular stock right now, how is it changing, how's the world changing, and how is the state of the trader itself changing through time. And I'll show you the rule set that allowed us to do that really good trade there. It's very complex and large, and in fact, this is an alternative representation to the neural network. We actually evolved this representation, and it is human readable. It's understandable, it's explainable, even though the AI actually designed this AI. Okay, so what am I getting at? My belief is that by using evolutionary computation in conjunction with deep learning and neural networks, you can expand our definition of AI beyond just building very robust models. Now your AI can be adaptive through time, and it can also be creative. And so here's another example of using a system like this. We took the state-of-the-art for image captioning. Give it an image and have it give you a natural language description of what's happening in this image. For example, for the blind. We took the state-of-the-art and we evolved it, and we exceeded the state-of-the-art. And you can see, even in cases where it got it wrong, it's not really that much off. We took the 25-year-old stable LSTM architecture, and we evolved it on a language modeling corpus. And you can see through generations how that particular cell and architecture kept getting better and improving and getting more complex, new memory cells, new feedback loops, and exceeding the state-of-the-art. And you can actually see this as the system is evolving deep networks through time, and it's improving on a multitask effort. This means learning one language, in this case, or 3 or 4 languages, allows the system to get better at other languages that it's trying to learn. And evolution of deep networks is allowing us to exceed the state-of-the-art from about 30% error down to sub 10% error. That's the difference between something that's unusable and something that's usable. But let's go to a completely different application area. In today's world, we are able to grow things in completely controlled environments. In hydroponics, in warehouse size, or in this case, a container-sized greenhouse that has no interaction with the outside world. I'm hoping that this, I think the video is a little slow. There you go. And, but we don't know how to do it. That's the issue. We do not know, after 10,000 years of humanity doing agriculture, if you take away the context, we do not know how to grow things. And now we can actually grow things more efficiently and tastier by modeling how things grow using neural networks and then evolving against that to come up with new recipes for growth. And this is what that would look like if the slide comes up. And by doing so, what we discovered is we rediscovered something we already know, which is that growing plants that are larger make them less tasty, but also something that we didn't know, which is that if you shine light on basil 24/7, it actually thrives. And people didn't know that. So an area where we can now grow and even solve things like world hunger and save on transportation and so forth using the combination of evolutionary computation and neural networks. Thank you very much.